I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. The lecture today, we're going to cover an introductory lecture into enzyme kinetics, which I think of as basically looking at catalysis, chemical catalysis in the biological world. So this is meant to be a follow-up on a lecture I gave on chemical kinetics, specifically looking at now what is very common in the biological world, which is the topic of enzyme kinetics. And so I first like to just remind us of general catalysis and how its effect on kinetics, or the time scale of reactions. And that we can have catalysis reactions. To catalyze a reaction is to do something that speeds up a reaction, typically through changing the activation barriers between a reaction. So it's not changing typically the thermodynamics, the overall change in, for example, the energy from the reactants to the products, the Gibbs free energy of whether something's spontaneous or not, but just the activation barriers, or the between the two states, to give you, in a sense, affecting the time scales at which these reactions happen. And so the most common catalysts, and these are whole areas within the chemical and biochemical sciences, can often be split up into numerous parts. In chemistry, it's usually whether it's a homogeneous or heterogeneous catalysis. In other words, are you using a surface like a platinum electrode to do some type of reaction where it's heterogeneous, the catalytic agent is separate in a sense from what's being reacted. Some things can regenerate, some things are used as part of the catalyst, etc. This is a whole area of chemical sciences, and a whole line of research goes into creating new catalysts for all sorts of chemically important reactions. Also, homogeneous reactions, where you're often putting something into the material itself, and it's homogeneously distributed, and it's just able to act as a way to get over these intermediates, these high energy activation barriers, and allow things to find its free energy minimum better. Or it's kind of shown here, uncatalyzed reactions can have very high activation barriers, and it's usually the catalysis that brings this down, and it can do it in a very simple way, or it can do it in complicated ways with multiple intermediates. And you can have heterogeneous things like surfaces, like platinum surfaces that catalyze, for example, the splitting of water reaction famously, or things that you add to things directly that are homogeneously in the system. And then what we're here to mainly introduce today is enzyme kinetics. And so this is, in the biological world, one of the most common types of catalysts. And so they're typically, enzymes are not always, but are often proteins. And they often do this, one of the most common types you see are these lock and key type enzyme to the substrate. So the substrate could react to form products on its own, but what this enzyme substrate complex does is lower this activation barrier significantly, so that the time scale of this substrate going to products is greatly enhanced through this lock and key type of mechanism. And what are we talking about as far as some of these? So let's look at a very simple reaction, something like peroxide going to water and oxygen. And if you look at it with no catalyst at all, it happens very, very slowly, right? So it takes very, very long periods. And as soon as you add, a protein catalyst to this, you speed it up, orders of magnitude, and it's because you've decreased its activation barrier from something like 70 kilojoules per mole all the way down to 8 kilojoules per mole. So at room temperature, this thing increases orders of magnitude in speed at which the reaction happens. So again, we go from something with a very large activation barrier to almost no activation barrier for it to be able to go from reactants to products in this. And so this is a good example, of an enzyme or a protein being used as a catalyst, that we therefore then call it an enzyme. And again, like here's showing you, so you speed up to 10 to the 6 inverse seconds for the one we just showed, but you can see some of these overall catalytic constants, or how much, the maximum velocity over its initial, normalizing to its initial substrate concentration. You speed these things up, often, thousands to millions of times faster than they happen naturally. This is a critical aspect in most of a lot of reactions in biological reactions are catalytically driven. And in this lock and key type mechanism, Michaelis-Menten kinetics is one of the most commonly followed, or the most commonly types of mechanisms which this substrate locks into an enzyme to form an intermediate, so that it has a rate constant to this enzyme substrate intermediate, and of course it has a back reaction, and that doesn't in any way have to be the same rate forward and backwards. And then now this second one has a rate forward to products. And usually, again, this could have a back reaction as well. It's just typically this is at a higher, so the energy, this is very, very slow with respect to the forward reaction. So it often gets neglected here. In fact, that's primarily what goes into Michaelis-Menten kinetics, is the assumption that this back reaction is very, very slow. So it's just looking at 3 out of the 4 potential rate constants. And the assumption is that K minus 2 is much, much smaller than K2, than the forward one. So that you don't have to consider it backtracking that way. You only have to consider the initial enzyme substrate forming. It can also sometimes unform, but if it does form this and does go on to products, you don't have to worry about the products re-reacting with the enzyme back. Okay, when you take that into consideration and look at some of the math, you can now define these 3 rate constants and redefine it as a Michaelis-Menten constant. And now we get an equation that we can plot in some way. And via its maximum velocity and its Michaelis-Menten constant is usually what we're looking for versus the substrate concentration you're starting with. There's several ways to look at this because it is complicated. The most common we show here, which is to plot the inverse of its of the velocity versus the inverse of its substrate concentration versus the inverse of its velocity that it's going at. And then we fit that to a line which we get related to where it crosses the x-axis, its inverse, its negative inverse of its Michaelis-Menten constant, and it's related to the maximum velocity that it would have at its highest concentration. So there are several other ways I include here that this can be looked at as well to try to get out what these constants are. And this helps, and then this is directly related to, as you saw in the previous slide, basically a ratio of the rate constants for K1 and the back reaction, and then K2, assuming the back reaction for K2 is slow. So this is the one of the most commonly used methods for looking at enzyme kinetics and what the overall rate constant, this ratio, would be in these systems. So hopefully this gives you an introduction to enzyme kinetics and a practical way of being able to plot and look at these rate constants when you have enzyme substrates in biological systems. Thank you.